If you drop an object from a certain height, its motion can be described by this general equation. But where does it come from? What does it mean? And are there cases where it doesn't apply? Welcome to Physics with Lucky. Today we are talking about free fall. Lucky insists this is technically a vertical throw because our formula includes an initial velocity. Fair point. Anyway, let's begin. First we want to derive the equations of motion, and for that we need a coordinate system. In this case, it's pleasantly one-dimensional. We only need the y-coordinate, which represents the height of our object, and that height changes with time t. And our object is this little red dot. Lucky also wanted us to be very clear about the assumptions we are making. We'll use Newtonian mechanics, meaning force equals mass times acceleration, and we assume the object is a point mass m, released from a starting height h. Later we'll use a concrete example, 10 kilograms from 10 meters. We are on Earth, so we take the gravitational acceleration as g equals 9.81 meters per second squared. Yes, g varies slightly across Earth, but we'll treat it as constant. Oh, and we'll assume no air. Vacuum. That's a lot of restrictions, but if we don't start simple, it gets complicated fast. In mechanics, the usual starting point is Newton's law. The acceleration is proportional to the sum of all forces, and the proportionality factor is the mass, F equals m times a. In our case, there's only one force, the weight force Fg. And yes, if you're thinking gravity isn't really a force, we are not doing Einstein today. You may have noticed force is a vector, and so is acceleration. So we can write everything in vector form. But gravity acts only vertically, so in the x and z directions, nothing happens. Reminder, height is our y direction. Gravity points downwards, so with up as positive, the force is negative in y. So we only need the y component and we can ignore x and z. How large is the weight force? Well, force is mass times acceleration. The acceleration is g and the mass is m, so Fg equals m times g. Lucky had prepared a 10-minute detour about inertial mass versus gravitational mass, but we'll skip that today. If you really want it, tell me in the comments. Now divide both sides by m. So from here on, m cannot be 0. And we get our equation of motion. A equals minus g. And what does it say? The acceleration of the object is the gravitational acceleration. Shocking. It's kind of trivial, many textbooks just write it down immediately. But something is remarkable. In vacuum, the motion doesn't depend on the object's mass. David Scott demonstrated this on the moon in 1971 by dropping a hammer and a feather. Both hit the ground at the same time. Or were the Americans never on the moon? Tell me in the comments. Alright, this is our equation of motion, and now we'll solve it step by step. The goal is an explicit expression for height y as a function of time. Acceleration is defined as the time derivative of velocity. Now we integrate both sides over time. On the left we get the velocity, on the right the antiderivative of the constant minus g plus an integration constant c1. To understand c1, note that at t equals 0 the velocity is the initial velocity. Plug in t equals 0 and you get v of 0 is c1. So c1 is the initial velocity and we rename it c1 equals v0. And thus, velocity is minus gt plus v0. But we are not done yet. Velocity is the time derivative of position. Same game again, integrate both sides over time t. Left becomes y of t, right becomes the antiderivative of v of t, plus a new constant c2. To identify c2, we use the initial position. At t equals 0 the object is at height h, plug in t equals 0, and y of 0 equals c2 equals h. So there's the final result, the equation of motion in all its glory. Lucky says we should explain that initial velocity term since it's not pure free fall. He's right. Let's visualize this with a height time graph. Let's start with free fall without initial velocity. So v0 equals 0. Then the formula simplifies to y of t equals minus a half gt squared plus h. Height decreases quadratically with time, exactly as you'd expect, until the object reaches the ground after fall time tf. If we have a positive initial velocity, that means we throw the object upward first. So it rises a bit, then turns around and falls. In that case, the fall time is longer. The last case, v0 is less than 0, we throw the object downward. No surprise, it hits the ground sooner. But how long is the fall time exactly? We can calculate it. The fall time is the time when the height becomes 0. So we set the equation equal to 0 and solve for tf. We'll multiply by -2 to make it look nicer and get this quadratic equation. So you solve it with the quadratic formula. The result has two solutions, one with a plus and one with a minus. So yes, one solution is a negative time. That would mean the object hit the ground in the past. We can philosophize about that in the comments, but for our problem, the physical answer is the positive root. Now we might also ask how fast is the object when it hits the ground. We can compute that too. The impact speed is just the velocity at the fall time, so Vf equals v of tf. If you plug the expression for tf into v of t, you get a long-looking term, but things simplify nicely. The g cancels and the minus v0 and the plus v0 cancel as well, and you end up with the final impact velocity. We'll do examples in a second. First, let's summarize what we have. These four equations describe vertical motion under constant gravity, including an initial velocity. If you plug in the starting height h and the local gravitational acceleration g, the motion is fully determined. But the validity is limited by our assumptions. They really apply only in vacuum and only over height ranges where g doesn't change much. For example, the International Space Station orbits at about 400 kilometers altitude, and there g is only about 88% of its value at Earth's surface. And for extremely massive bodies or relativistic initial speeds, these equations aren't sufficient. Same for elementary particles. But for everyday situations and a few meters of height, they work very well. Their biggest advantage is simplicity. And if there's no initial velocity, it becomes even simpler. Let's look at a few examples. First, our example from the beginning. We drop a 10 kilogram mass from 10 meters height. So basically a very heavy cat from the third floor in vacuum. Yes, no. Lucky says you absolutely should not do that, and he's right. So let's use a big sack of potatoes instead. The sack hits the ground after about 1.4 seconds, and its speed is about 14 meters per second, so roughly 50 kilometers per hour, and that's already pretty serious. If we didn't drop it, but instead threw it upward at 50 kilometers per hour, very unrealistic but still, then it would take about 2 seconds longer and the impact speed would be over 70 km per hour. And interestingly, that's exactly the same impact speed you'd get if you threw it downward at 50 km per hour. It just happens faster. After about 0.6 seconds, the sack is on the ground and the potatoes are not having a good day. Now back to the case without initial velocity. Let's increase the drop height to 185 meters, about the height of the European Central Bank Tower in Frankfurt. Now the sack falls for about 6 seconds and hits at about 60 meters per second, which is over 200 kilometers per hour. At that point we are not really talking about potatoes anymore. Put the same tower on the moon and the impact speed drops to about 86 kilometers per hour. Moon gravity is only 1.62 meters per second squared, much less than on Earth. So it accelerates more slowly and the fall takes longer, about 15 seconds. And finally, let's go extreme and put the tower on the surface of the sun. Yes, I know you can't, but if you could, the fall would be over in a bit more than a second, and the potatoes would hit at about 318 meters per second, over 1000 kilometers per hour, almost the speed of sound. And at around 6000 degrees. Those are not even fried potatoes anymore. At that point, the object breaks down into its atomic ingredients. That's the end of our little video. And this, by the way, is Lucky. And I'm pretty sure he's already thinking about the next one. Because next time he wants to show what changes when we are not in vacuum, when air resistance comes into play.